I said just now, right? So this is a typical CMOS. This is the old one, right? Pretty old, about CMOS. You have a substrate, which is P-type, mostly hole. Then on top of it, you form the NMOS. Then you have an N-type source and drain and P-type substrate. You also need to connect the P-type substrate to a contact, otherwise it will be floating. How do you realize PMOS and NMOS on the same wafer? You will do an implant to form the N well. So this is N well because it is an isolated region in the substrate, which is N-type. So inside this well, you will put the P plus here to form the source and drain. And again, you need to electrically connect the N well to somewhere. So you need to N plus to connect it. And this becomes a PMOS. Are you okay with this? But this is a very old style. Now then when you go to early 2000, maybe up to 45 nanometer or 65 nanometer technology, you see a lot of innovation. I will just verbally say what they are. If you can follow or you can memorize, that will be great. First of all, we have metal gate. In the past, you used polysilicon. Why do we use metal as the gate? Do you know? Just guess. What's the good thing about metal? Very good. It has smaller resistivity. Rho, I discussed last time in last class, right? The electrical resistivity. It also has something called high K dielectric. Instead of using silicon dioxide, you use something like hafnium dioxide. What does it mean? The capacitance of an insulator, if you forgot, go back to review, equals to the permittivity divided by the thickness. And depending on the material, you have different relative permittivity. For example, for silicon dioxide, the relative permittivity is 3.9. For hafnium dioxide, it depends, but let's say it's about 30, for example. It's about right. Depends on the process. What does it mean to the capacitance? If I use a material that has a higher permittivity, what happened to the capacitance? Based on this equation I just wrote, you'll be higher, right? I should also say higher for the same thickness. I can get a larger capacitance if I reduce the thickness. I can make this very thin, then I have a very large capacitance, right? But what is the problem of making this layer very thin? When you make something very, very thin, what's the problem? Say again? This is the capacitor insulator. So we want it to be high resistance, right? To be not conducting. So quite opposite. When you make it very thin, what happens? Huh? Have you heard about quantum? Yeah. Hello. So I don't know if you're aware of this, right? When even you have an insulator, when it is very thin, you might have quantum mechanical tunneling. Have you heard about this? Yeah? So, okay, very, very good. So, for example, there is a door, even it's closed. If I'm a particle, I hit it, I have finite probability to go through the door. Even my energy is smaller than the breaking power. Okay? That is called tunneling. Like you tunnel through a mountain. You don't need to go through the peak. You don't need to gain the kinetic energy you need or the potential energy you need to go over the barrier. For the energy you have like here, this one has very low energy, but it is much lower than the barrier. I still can go through with finite probability, right? So in principle, if I try 1 trillion, quadrillion, many times to run into the wall, there's a finite chance that I can go through the wall without problem. But just for macroscopic object like us, we have the quantum decoherence, we cannot achieve that. But for particle like electron, you can do that. So when this is very thin, then you run into problem. You have a lot of leakage current due to tunneling. So later we are going to study saying that this one need to act as a capacitor. We don't want to have a gate current through it. And that's why in the early 2000s, people change silicon dioxide to hafnium dioxide or something called high K dielectric. So this K means copper, which is epsilon R, means they have very high dielectric constant. And that is the standard now in the industry for the advanced technology node. We also have something called silicide. This is to reduce the contact resistance. It is a metal react with silicon, right? So this one is to reduce what I call rho C, contact resistance. Okay, we want to reduce it. You see, all the purpose is to reduce the resistance to make our transistor interconnect better. Now, besides of this, you will also see that besides source and drain, I have some extension here. So, and somehow they put N++. There are some, really depends, but this extension, sometimes it's actually nicely doped, right? I would just call this LDD, lightly doped drain. We won't go into detail. The reason is to reduce the hot carrier, hot electron, to smooth out the electric field. Otherwise, your electron may have too much energy. You will go over the barrier and get trapped by the oxide, and that would degrade your transistor. Okay? Now, this drawing is not good. They try to put P plus here. It's a little bit, maybe not that standard. What exactly it does is this. You have a transistor. You have the N plus. You also have some LDD. But then you actually will do some pocket implants so that in this region, you have some P-type. And this is called halo. And it's easy to understand why it is called halo, because it is in that, like a halo, right? But the main purpose is this. Remember, the substrate is P-type anyway. We try to add some large P-type here is to avoid the punch through, because when the channel is very short, your source and drain are close to each other, you will get a lot of leakage current through the bottom. Okay, so the halo are there to avoid the punch through. You need that for planar device, but in this class we'll also discuss the SOI and FinFET. In that case, then we don't need that. We will see that later. But I hope you will, maybe you cannot memorize, right? But in the future, compared to the slides, some key things about a real transistor: metal gate, high K dielectric, silicide, extension, and halo. Plus, you need to add stress strain to enhance the performance. Right? And that is something you can spend the whole semester to study for device physics, but we won't do that. That is not the purpose of the class, but I want you to be aware of that. Any questions? Okay,